Today, as a part of the CS Plus program, we are part of the blockchain and cryptocurrencies team, and we're going to run through what we did this summer.
Hi, I'm Dylan Paul. I'm a rising junior at Duke University, majoring in computer science with a concentration in AI and machine learning, as well as a minor in finance.
Hi, I'm Oum Lahade. I'm a rising sophomore at Duke studying electrical engineering and mathematics with a minor in finance.
Hi, my name is Malika. I'm part of class of 2024. I'm majoring in economics and computer science and doing the markets and management certification.
Hi, I'm Rhys Banerjee. I'm a rising junior at Duke, majoring in computer science with a concentration in AI machine learning and minoring in mathematics.
So to begin with, we'll provide an overview of the internet computer, which is what we were developing on top of for this whole summer. So the internet computer is essentially the third iteration of blockchain technology, and it's a distributed ledger technology that enables the creation of applications that are permissionless, secure, transparent, and borderless. So the internet computer essentially is just a highly scalable version of the Ethereum network, and it utilizes canisters, which are essentially analogous to Ethereum smart contracts and are executable code contracts that run on top of the blockchain. Ultimately, the hope for the internet computer is to create a completely decentralized version of the internet, and what we've been building on top is a decentralized banking app, or two decentralized banking apps.
So just a couple of definitions before we start. What is DeFi? DeFi, also known as decentralized finance, is a type of finance using blockchain, but without any financial intermediaries. So centralized finance, on the other hand, such as like brokerages, exchanges, banks, they rely on intermediaries. So what opportunities does DeFi present? In general, DeFi increases transparency, scalability, interoperability, and accessibility.
Now we'll be discussing the two different types of protocols. So first, what are lending protocols? Lending protocols allow users to deposit assets into liquidity pools. The protocol will then take those funds and lend them out to borrowers. Next, what are borrowing protocols? Borrowing protocols allow users to take out over-collateralized crypto loans at a 0% interest rate by depositing assets and withdrawing a protocol-generated stablecoin. Now, lastly, why do we care? The DeFi poses an interesting solution to the problems of centralized financial systems. So by studying DeFi, we can determine the future of finance.
Throughout the summer, we actually worked on two separate projects, both related to DeFi and DeFi field. Malika and I worked on ICy, which is a decentralized lending protocol, and Oum and Rhys worked on Waterpark, which is a borrowing protocol. So first, we're going to dive into ICy, and then Oum and Rhys are going to discuss their Waterpark protocol.
So Aave is a decentralized lending protocol on Ethereum, and that was our main inspiration for this summer. However, instead of creating this protocol on Ethereum, we wanted to go ahead and create it on the internet computer. Aave is a way for users to lend, borrow, and earn interest on any crypto assets on Ethereum without any intermediary, which is pretty huge considering centralized finance programs always have intermediary involvements. So Aave was launched in 2017, and it's since found much success, as you can see with its large closing prices and value locked. And just like what exactly is a lending pool, a lending protocol helps connect lenders and borrowers through a pool of assets instead of transferring directly from a specific lender to borrower. And when borrowing, a user locks up collateral more than what they borrow. And then once a user deposits collateral for lending or borrowing, they're given A tokens which receive interest. So Aave also has some other cool features such as price oracles, flash loans, arbitrage opportunities, but those we did look at and they are more specific to Aave itself. So just some quick advantages and disadvantages. Some of the pros of Aave are that it serves a wide range of DeFi applications and most cryptocurrencies as well. So that's why it has such a large audience. Aave provides collateral-free flash loans as well as fixed fee flash loans. And that is incredibly helpful to all of their users. Some cons are that it's not super beginner friendly. You'd need to know a good bit about cryptocurrencies, blockchain, and Ethereum. There's also a large transaction time, so about 5 minutes, and there's over collateralization and high transaction fees. So this summer, Dylan and I looked at a couple key technologies on the internet computer. So to start with, chain and key technology is actually quite complicated, but it is incredibly useful and is one of the big differing factors of the internet computer versus Ethereum. So chain and key allows the internet computer to finalize transactions in a matter of seconds, and every node has a canister with secret key shares. So when you combine those key shares, you create a message for the public nodes and key shares to share and execute. And then the NNS is the open governance system that manages the internet computer. So it does like everything a governance system should do. So it'll store what nodes belong to its subnets, update them, and it can be used for like price oracle canisters, which we use with Project ICy.
And gas is the transaction fees that must be paid to ensure functionality of both blockchains. The reverse gas fee model on the internet computer comes in direct contrast to what is seen on Ethereum's blockchain, where they have the gas fee model. The reverse gas fee model puts the onus on developers to pay for transaction fees rather than users, which tackles the current problem of high transaction fees that users are facing on Ethereum, where they can face upwards of $50 of transaction fees for each transaction they make. Developers on the internet computer pay for their canisters or smart contracts, computational costs, and ongoing persistence of memory using cycles, which is analogous to gas on Ethereum. And this enables users to access applications for free, and more specifically, our decentralized lending protocol, ICy, for free. So ICy, which stands for Internet Computer Yield, acts as a decentralized lending protocol in a similar fashion as Aave does, but specific to the internet computer. ICy allows users to lend and borrow assets that are native to the internet computer, so ICP tokens and cycles, and takes into consideration users' collateralization ratio. Receipts for users' transactions are given in terms of AICP and A cycles, which are minted and burned by the protocol itself, and these tokens can earn interest as well as show proof of ownership to redeem deposited assets and can be held as collateral to borrow the opposite asset. ICy will also utilize a price oracle feed for exchange rate of these two assets. Now, ICy differs from Aave in a couple of ways too. To utilize the features of the product canister, which once again is a smart contract that has all of the lending and borrowing features, users must open accounts and supply these accounts with funds from their personal canister or their wallet. This design was to combat the current lack of standardization of tokens on the internet computer blockchain. Additionally, the price oracle feed comes from the network nervous system, as Malika discussed, rather than a source like Chainlink. And last and most important, there are no transaction fees for users due to the reverse gas fee model structure. This solves the high transaction fee problem faced by users on Aave, which consistently inhibits users' abilities to make transactions. So here are some screenshots of the candid UI interface, which the internet computer provides to test out functionality of the backend of the code. And here you can see two primary functions. On the left, we have a treasury, which mints and transfers funds to users so they can test out interactions with the protocol. And on the right, you can see that users are depositing to the protocol and receiving A tokens as receipts.
So we have a couple front end pages too that we created. We have like a user page and about page, and you can see on the user page, we have a couple sample functions that the user can input data on. So like, for example, I could create an account, view my ICP balance, cycle balance, mint cycles ICP, transfer cycles in ICP, and withdraw. And then this is just like a demo, so it has some variables inputted in where, and then over here on the about page, you can learn more about like the canisters we use and what exactly ICy is. And then lastly, the developers page just to let you know a little bit about us.
And for more information, here's a link to our GitHub repository with the current code for the ICy protocol, as well as a link to the warp wire demonstration.
All right, so now we'll transition into me and Oum's project. We worked on Waterpark, a borrowing protocol for the internet computer.
So to provide a bit of background on Waterpark, essentially the system generates stablecoins titled SDR against ICP as collateral, not Ether. The main motivation behind this is the price volatility experienced by ICP, which is similar to the price volatility experienced by Ether, which you can see on the top right graph over there. And so here, essentially the main motivation is that although Ether is very volatile, stablecoins are created in order to develop stable smart contracts on the Ethereum and IC and internet computer networks. And so the system will generate a stablecoin that is over collateralized by the native token of the internet computer, which is ICP. And so users will deposit ICP into individualized troves, which can be considered as debt accounts on this protocol created for their specific user. And these troves are over collateralized at a rate of 110%, which means that users can essentially deposit $110 worth of ICP and withdraw around $100 worth of SDR tokens. This is extremely capital efficient compared to other current borrowing protocols on the Ethereum network. And then finally, SDR tokens will offer the basis for creation of stable smart contracts on the internet computer network, which should offer an ability to create a decentralized financial infrastructure on the internet computer as well. So the Waterpark protocol borrows a lot from the Liquidity protocol on the Ethereum network. In general, the major thing that it takes from the Liquidity protocol is the architecture of the system. So this is all of the troves, stability pool, ERC20 style token, and liquidation mechanism. So once again, troves are essentially debt accounts where users will deposit ICP and be able to withdraw SDR tokens. The stability pool is a mechanism used to maintain the stability of the entire system in case multiple troves fall into default. The ERC20 style token enables the creation of a stablecoin that can be traded on other exchanges. And then finally, liquidation monitoring is used to close troves that are in default in order to keep the system solvent. Finally, Waterpark also uses the LUSD stablecoin general stability mechanism. And so this is the stability mechanism used to ensure that the stablecoin is actually stable and is highlighted in red on the graph to the right. Although Waterpark pulls a lot from Liquidity, there are fairly different features between the two things. So the first is obviously use of a token pegged to the SDR or the IMF special drawing rights token, as opposed to Liquidity, which uses a stablecoin pegged to the US dollar. Secondly, the stability mechanism for the system as a whole is slightly different, with Waterpark using accounts that users can deposit SDR tokens into and provide stability to the pool, rather than Liquidity, which uses a dividend token to reward users. Finally, Waterpark also offers the ability to use a front end created by the developers rather than Liquidity, which requires further development for front end by other third parties.
All right, so here we'll see the front ends, both front ends for Waterpark. So on the left, we'll see the Candid UI front end, which, as Project ICy explained, Candid UI is the native web interface for the internet computer. On the right, we'll see a proof of concept that I created in HTML and JavaScript, depicting a proof of concept for a Waterpark homepage. However, it's not complete yet. So if you'd like to check out our code, we have a GitHub repository. And if you'd like to see a WarpWire demonstration video outlining the demo for Waterpark, then you can click the WarpWire link below. Next, we just like to briefly touch on the research proposals that all the students did. So Oum and I focused our research proposals on orthogonal persistence, where we asked questions such as how do differences in persistence alter the storage efficiency of Waterpark, or how do Dfinity's implementation of orthogonal persistence scale compared to existing decentralized data storage solutions. Dylan focused his research on gas models, where he compared the gas model on Ethereum to the reverse gas model on the internet computer. And then lastly, Malika focused her research on on-chain governance and liquid democracy, analyzing the differences in the governance protocols on the internet computer and Ethereum. So thank you. Thank you for watching our presentation. And if you have any questions, we'd be happy to answer.